Good day, Dr. Vayu and Dr. Vanzairin. I am Arul Bharati Radhakrishnan and will be covering up the introduction for this presentation and also steam methane reforming process description and finally with wastewater treatment plant process. Thank you.
Hi, I'm Eddie, the team leader from Group 6. So today I'm going to present you the three alternatives that we have come up with before the plant design process and followed by the control and the instrumentation system and eventually on the cost analysis on the plant.
I'm Ms. Chiu from Group 6. I'm going to present about the detailing process description for Unit 100, which is the ammonium scrubbing process, as well as the overview plan layout for our plant design projects.
Hi, my name is Mohammad Yazid bin Zulkifli and I'm going to explain on the safety and loss prevention of hazard study of Node 1 and Node 3.
Hello, my name is Salman Latif Chaudhary. My metric ID is 24801 and I'll be presenting Note 2 of the HAZOP study as well as the regulation limits and the tertiary treatment for the wastewater treatment plant. Thank you.
This is the outline of our presentation today. Moving on to the introduction part, which covers problem statement and also objectives. Firstly, problem statement. The Environmental Quality Clean Air Regulations 2014, or also called CAR 2014, has set specific emission limit for certain components. However, for our scenario, carbon dioxide and sulfur dioxide exceeds the emission limit that's set by CAR 2014. Hence, it is necessary for us to design a system to reduce the emission. Moving on to the objectives. There are two objectives for our project. The first one is to reduce the sulfur dioxide emissions from the flue gas to the environment so that it will meet the regulations of CAR 2014. And the second one is to produce at least two value-added products via conversion of gases such as sulfur dioxide and carbon dioxide to marketable products.
Right now, let us proceed to the conceptual design. So basically at this section, I'm going to show you three alternative design and I'm going to make comparison in terms of the cost mainly and to show you which one is the better selection. Allow me to introduce you the alternative one. So this is basically the simple plot diagram for the alternative one. So for the first unit, what we have here is basically the SO2 stripping from the flue gas, for which we are using the sodium sulfate. And this unit is known as the Wellman Lord. And after getting the SO2, we are basically sending to the next unit, which is the contact process. And we are producing our first value-added product, which is the sulfuric acid. And the CO2 with other impurities is going to descend to the next unit, which is the CO2 purification. So as the name suggests that we are purifying our CO2 by using this unit, which is the potassium carbonate scrubbing. And after getting the CO2, we are sending to the next unit, which is the methanation. So for this methanation, we are actually producing our CH4, which is the methane, but we require H2. So at here, we are basically using the water electrolysis to produce the additional hydrogen to support this process. So for this methanation process, we are facing a little bit of a dilemma. So in terms of the CH4, we are not sure whether we are going to sell it directly or we are going to feed inside a gas turbine and feed it and become or convert into the electricity. So we make some comparisons. So in terms of the CH4 direct sales, we are actually making money of 271 million RM per year. In terms of the electricity sales, we are only making 204 million RM per year. So basically, just based on this calculation, we determine that the CH4 direct cells would be a much better selections. So moving on next, which is the H2 production. So in terms of H2 production, we are using the water electrolysis. There's actually two options. One, it's without the renewable energy. One, it's with the renewable energy. And it is determined that with the renewable energy, it's actually losing more money in comparison to the renewable energy. So it means that if let's say we want to produce H2 through water electrolysis without the renewable energy, is a much better selection. It is because this renewable energy has a much higher investment cost because of the installations of the solar panel. So that's all for alternative 1. So right now, allow me to introduce you the alternative 2. Let us look into the details of the alternative 2. So at the first unit, instead of using a sodium sulfate, we are using the ammonium hydroxide to actually absorb our SO2 to produce our ammonium sulfate, which can be used as a fertilizer. And then for the CO2 purification unit, we are using the sulfonyl unit with a solvent of dipa, diisopropanoamine, sulfolane, and also the water. So moving on next, the CO2 is going to send to the dry methane reforming, supported by the steam methane reforming to produce the methanol, which is our second value-added product. So right now, let us look into a little bit about the cost of the alternative 2. So in terms of the ammonium sulfate production, the ammonium purchase will be around 40 million Rm per year, and for the ammonium sulfate cells, right, it's around 90 million Rm per year, which means that the sales is actually more than the purchased, which means it is a profit. In terms of the methanol productions, the CH4 purchase will be around 2.5 million with the methanol sales of 2.5 billion, which means it's able to cover the CH4 purchased. After the alternative 2, our group has actually proceeded with alternative 3. In terms of the alternative 3, it's basically the combination of the alternative 1 and 2. So what we have for the first unit is basically by using the sodium sulfate, we are going to absorb our SO2 and we are going to send to the next unit, which is the contact process to produce the sulfuric acid. And moving on next, which is the CO2 purification by using the potassium carbonate, and then the purified CO2, it's going to move to the next unit, which is the dry methane reforming, supported by the steam methane reforming to produce the methanol. So in terms of the cost evaluation of the alternative 3, what we can see here is that the sulfuric acid sales will be around 11.7 million, and with the methanol production sales of 2.5 billion, and the CH4 purchase will be around 4.26 million. So from what we can see here is that this alternative at this point it's still profitable. So right now let us compare between the alternative 1, 2, and 3. So basically, let's see the EP1. In terms of EP1, alternative 1, it's actually making a loss of negative 2.4 billion Rm per year, which means that alternative 1 will no longer be taken into consideration. How about comparing between 2 and 3? So let us see the EP1 after considering the cost of the solvent. It determined that the alternative 2 is still making profit of 2.35 billion Rm per year, and on the other hand, alternative 3, 2.45 billion. So it means that they are both still making profit. Right now, let us take into the utility cost into consideration, and it's determined that alternative 2 is still making profit of 580 million Rm per year. And on the other hand, alternative 3 is losing money of 1 million Rm per year. So it means that alternative 2 will be selected. Here, I'm going to show you why alternative 2 is a much better selection in terms of the operation wise. So for the first unit, which is the SO2 extraction unit. So first, alternative 2, we have the ammonia scrubbing, and alternative 3, we have the Wellman-Lord. So basically, ammonia scrubbing is a much better selection because it can straight away produce our ammonium sulfate, whereas the Wellman-Lord, it has to go through the contact process, which is a whole unit, which means that Kpads and Opads increased. So alternative 2 is selected. In terms of the cost analysis, alternative 2 is a much better selections. And alternative 2 and 3, they are actually both meeting the CAR 2014 requirement. And eventually, we have the CO2 purification unit for which sulfonyl unit and the potassium carbonate, it's being compared. And in terms of the operations, sulfonyl unit is a much proven technology because potassium carbonate is actually causing corrosion to the equipment, clogging of the tray column, and so forth and on. Right now, let us proceed to the simple reactor optimization. So firstly, let us look into the methanol reactor optimization with a tag number of R501. So prior to that, we have actually done some literature review, and there are two configurations being proposed. One is a direct and one is indirect. And it is determined that the direct is actually better than the indirect cooling because as shown by this graph, it is determined that the methanol formation rate for the direct cooling is actually much better than the indirect. And at last, we have the proposed design of this for which the reactor is actually surrounded by the cooling water cooling so that the temperature of this reactor can be ensured and fixed. So not only the configuration optimization, we are looking into the equilibrium reactor data that's based on the Lim et al. 2009. And based on the icon simulation running, it is determined that, it is proven that the optimum pressure will be around 75 bar with a CO conversion of 99.57. So basically this 75 bar, it would be our operating pressure of our methanol reactor. And thus our reactor optimization is achieved.
So for this part, I would like to present about the details process flow descriptions that is involved in our selected conceptual design alternative, which is the second alternative. For Unit 100 process flow diagram, which is the ammonia scrubbing process, basically the flue gas from the thermal oxidizer will react with the ammonium hydroxide to form ammonium bisulfate in the absorber, and it will then oxidize in the oxidation tank to form the wet ammonium sulfate solid. And this wet ammonium sulfate solid is then transferred to the hydrocyclone in order to remove and recycle the unreacted gas back to the absorber, while at the same time the wet ammonium sulfate is then sent to the dryer in order to form a dried ammonium sulfate solid fertilizer, and the water removed from the dryer is then sent to the wastewater treatment plant.
Thank you, Min Chen, with the introduction. So right now I'm going to proceed to Unit 200. So basically for this Unit 200, it is for the CO2 purification. So here the inlet feed, it's mainly consists of the CO2 and also other impurities. So the CO2, it will reach this absorber and it's going to be absorbed by the solvent here. So basically the solvent used will be 50% of the diisopropanyl amine, 25% of the sulfolane, and 25% of the water. So together with the CO2 and also the sulfolane, it is known as a rich amine. It's going to be heated out and also sent to this distillation column. So this distillation column is basically a regeneration column for which the CO2 will be stripped from the solvent and sent to the next unit, and then the lean solvent is going to be recycled back to the absorber. So from here you can see that there will be two highlighted streams for which heat integration is being performed between the rich solvent line and also the lean solvent line. So through heat integration, it is determined that the total saving that can be achieved from this integration will be approximately 20 million per year.
This is the process flow diagram for Unit 300, which is about steam methane reforming process. So for this process, the water heats up and enters the reactor, while the methane also enters the reactor, and the reaction takes place in the reactor, and the syngas is produced out from the reactor. It's then cooled and goes to the flash to separate the water, and the syngas in the gas phase goes to the next unit, while the water goes to the wastewater treatment.
Hi, this is Salman. I'm here to explain the heat integration for the Unit 400 or dry methane reforming unit. For the fired reactor R401 to work, a temperature of 1000 degrees Celsius is required. Yet the carbon dioxide that is coming out of the K401 compressor is at 130 degrees Celsius. By combining the cold and the hot stream that is coming out of the R401, the temperature of the inlet stream could be brought up to 980 degrees Celsius. Thus, the energy is saved as less fuel is required to raise the activation energy required for DMR reaction to occur. The same could be said when the hot stream in stream number 6 comes in contact with the cold stream in stream number 4. The heat integration reduces the temperature in stream number 5 to less than 200 degrees Celsius. In here, the cold utility cost is significantly reduced, as the E402 heat exchanger do not have to use up as much cooling water for lowering the temperature. We have performed heat integration on Unit 400 with the minimum approach temperature of 10 degrees Celsius. This slide shows our calculations and energy savings. Before heat integration, our energy consumption was at 145 megawatts, while after heat integration, our consumption for this specific unit reduced to 31 megawatts. Consequently, the monetary savings from just this one unit add up to 5 million ringgits per year.
Hi, so I'm going to explain on the process flow diagram of Unit 500. So here we have a methanol reactor that contains copper, zinc, and turning mostly carbon monoxide and carbon dioxide as well as hydrogen into methanol. This process is in 160 degrees Celsius, which is a hot uh, process. So after it is leaving out, it will then be condensed into vessel V5O2, and the remaining will then be recycled back into the inlet stream of the reactor by using compressor K5O2. So this compressor needs to be heated up, whereas the outlet of the reactor needs to be cooled down. So as you can see, there's a heat integration going on between these two streams.
Thank you, Yazid. So without further ado, let me proceed with the instrumentation and the control system. So basically in this section, I'm going to talk about the basic control strategies that we have implemented to ensure that our operation is smooth. So for the first unit, which is unit 100, so the special control strategy that's being implemented here is basically at the cyclone here, for which ratio control is being implemented. So basically this ratio control is try to control the pressure ratio that's between the overhead and also the underflow discharge pressure to ensure that our cyclone is operating at the optimum condition. So moving on next, which is the unit 200. So what we are trying to look into here is basically the regeneration column, which is C202. So firstly, what we have here is basically the feedback control. So the feedback control here is trying to control the pressure of the regeneration column. So basically, if let's say your pressure here is too high, so this controller, it will open the pressure relief valve here in order to vent out the excess gas so that it can relieve the pressure. So moving on next, which is the feedback control loop as well in order to control the level of the reflux drum. And lastly, which is the cascade control. So for this cascade control, what it's trying to do is it's trying to control the temperature of this column by controlling the LP steam flow at this point. So basically, if let's say your temperature is too high, what this cascade control is going to do is that it's going to lower down, or it's going to tune down the LP steam supply so that the steam supply is being lowered and result in the lower temperature of this column. So moving on next, which is the unit 300. So basically, there are two special control systems that's being implemented around this reactor 301. So firstly, which is the ratio control. So what this ratio control does is, here you can see there's a feed of the fuel, which is methane in this case. So what it's trying to do is trying to control the ratio between the fuel and also the air. It means that how much fuel is being fed inside is going to require a certain amount of the air. So to ensure that a complete combustion is occur, so this ratio control is needed. However, we cannot always ensure that this ratio control is working well. So here we need a override control. So what this override control does is that it's going to monitor the oxygen reading. So if let's say your oxygen reading here is too low, so it means that your air supply is not enough, and there's a lot of impurities that's going out, which signal that it is incomplete combustion. So override control will override the system and it's going to supply this air for the complete combustion to occur. So moving on next, which is the unit 500. So here we are going to look into the distillation column C501 and also the reactor 501. So for the distillation column C501, here we have the split range control. So what this split range control does is basically to control the pressure here. So what it does here is that if let's say we know that our pressure it increases is due to the buildup of the vapor that's at this process stream here. So what it does first of this split range control, if let's say there's a buildup of the pressure here, the first step is it's going to increase the speed of the air cooler here in order to maximize the rotations of this motor. So if let's say our pressure is still too high, then the pressure relief controller valve, which direct the excess vapor to the flare, it will be opened. So moving on next, which is a simple feedback control loop to control the level of this vessel 505. And lastly, which is the cascade control. So for this cascade control, like I've explained just now, we are trying to control the temperature of this column by controlling or tuning up or down of the LP steam supply here. Moving on next, which is the methanol reactor control system. So here we have the cascade control. So here this is the isothermal reactor. So basically, if let's say our temperature here is too high or too low, it's going to be cascaded to control the flow rate of the cooling water supply here. So moving on next, which is the feedback control. So this is our inlet. So what's happening here is that if let's say our pressure is too high, so what it does is it's going to open the relief valve here in order to send off the vapor to the flare system. So lastly, let me show you the compressor control. So this is the most common control that we can see in literally every compressor, which is the feedback control. So the valve here used is basically the anti-surge valve. So what it does here is basically it's trying to maintain the minimum flow rate of the compressor to avoid any surging to occur, because it could cause damage to our compressor. So moving on next, which is basically the feedback control as well. So for this feedback control, it's trying to control the discharge pressure of the compressor. So provided the pressure is too high or too low, so all it does is going to control the speed of this motor in order to control the duty of this compressor. So lastly, which is the vessel 501, we have the feedback control as well in order to maintain the level of the suction drum. So that's all from me for the instrumentation and the control strategies. Moving on next, let us present on the safety and loss prevention. At this section, the hazard will be presented by Salman and Yazid, and later on followed by the plan layout by Min Chen.
Hi, my name is Mohammad Yazid bin Zulkifli, and today I am going to present on the safety and loss prevention for hazard of Node 1 and 3. Node 1 is the methanol gas liquid mixture of distillation column. The node includes vessel V504 and the liquid line from the vessel to the distillation column. Next, this node also includes the liquid line at the bottom of the distillation column and the liquid line at the reboiler and the reboiler E506 itself. This node also includes the entire section of top part of the column, condenser E505, vessel V505, flare system, pump 501 and tank 501. So let's begin with the hazard study. I will present only one parameter failure due to time constraint. So the first is no flow. This occurs when FCV 502 fails or starts closed during normal operations. When this occurs, there will be no liquid flowing to the distillation column. Hence, the entire column level will decrease, causing an existing safeguard of level indicator alarm to trigger. Personnel will be notified and the bypass valve will be open. There will be no significant hazardous safety issues. However, to prevent this from occurring, regular preventive maintenance of FCV 502 is essential, as well as a proper and effective standard operating procedure for personnel when level alarm triggers. So this is the summary of the hazard study of Node 1.
Hi, this is Salman. Moving on to Node 2. The study area's main component is the methanol reactor R501 and the surrounding valves, instrumentation and control devices around the reactor. It also contains the K501 syngas compressor. FCB 501 controls the feed, while FCV 506 controls the cooling water going into the reactor. As the HAZOP study is much too long to cover in this presentation, let us look into one example. When the control valve FCV506 that supplies cooling water is stuck closed, then the exothermic reaction will increase the temperature inside the reactor. This will in turn increase the pressure, leading to a pressure valve being opened to the flare. This is why we have added a bypass valve as a safeguard and a temperature indicator controller to maintain the temperature of the reactor. We would recommend regular maintenance of FCB 506 so that this kind of incident will not happen.
Thank you, Salman. Hi, this is Yazid again. Let's proceed with Note 3. Note 3 is a distillation column of C2O1 for flue gas absorption of CO2. The node includes the vessel of V2O2 and the gas lines entering the column C2O1 from the vessels. It also includes the off-gas line at the top section of the column and the rich solvent liquid line at the bottom of the column entering the heat exchanger E2O2. The node also includes the lean solvent line loop from E2O2 back to the column. The cooler E2O5 and pump 2O3 is also included. So let's begin with the hazard study of Note 3. There will be no flow when pump 2O3 trips or FCV 2O2 fails and close. Lean solvent will not recirculate in the column, leaving carbon dioxide freely escaping to the atmosphere. This will cause environmental penalty as a consequence. The only existing safeguards available is the CO2 concentration indicator alarm, which trips and notifies personnel to open the bypass valve. A spare pump is required and critical to prevent such event to occur. Thank you. This is the overview and the summary of HAZOP Note 3 study. That is all for the HAZOP study. We will proceed with the plant layout. Thank you.
Thank you, Mr. Yazid, for his presentations about the HAZOP studies. So moving forward, I would like to present about our plant layout. So basically, our plant layout could be divided into three parts. And the first part is the technical building complex in which all the maintenance works could be carried out. And the second part is the administration's management office in which all the managerial matters could be carried out in this area. And the last one is the production side, which comprising of storage tank farm as well as the wastewater treatment plant. There are total of 3 emergency assembly points that are set up throughout our plant. This is to ensure a smooth evacuation of the personnel in case of emergency scenario take place. And our flare system is installed to be far away from our production site so that to minimize the risk of explosion that could be caused to our production site.
This section is about wastewater treatment strategy, and also it covers about the waste identification and the design of wastewater treatment. Wastewater treatment plant is designed to treat effluent before being discharged into rivers, seas, or any water catchment areas. It mainly operates to remove suspended and dissolved solids, ions, or any microorganisms, and also helps to reduce water pollution. So our effluent discharge quality shall meet standard B regulations set by the Environmental Quality Act 1971. For the waste identification, for each unit, we have also identified what type of waste and components it is made up of. And we found that mostly it is water, carbon dioxide, nitrogen, hydrogen, methanol, methane, and carbon monoxide.
Hi, this is Salman. Moving on to regulatory limits. Here are some of the regulation limits that we are following for our wastewater treatment. According to the regulation, Environmental Quality Act 1978, the oil and grease concentration should be below 10 milligrams per liter, while the biological oxygen demand should be below 50 milligrams per liter. The plant produces virtually no suspended solids, so we don't have to worry about that aspect. As shown in this slide, most contaminants are in gaseous form, so they will be easily removed by the dissolved air flotation, the DAF, aeration tank, and the clarifier. But it is imperative for methanol to be removed through the wastewater treatment plant. The methanol contributes most significantly to the concentration of oil and grease and the biological oxygen demand as well as the chemical oxygen demand, which is detrimental for the overall quality of the water. This is why our wastewater treatment is more designed to remove methanol from the effluent stream.
This is our designed process flow diagram for our wastewater treatment plant. According to Department of Environment, there are several levels of wastewater treatment that we need to consider to design the plant. In this section, the first stage is preliminary. Preliminary treatment is important in removing large solids which may harm the mechanical equipment and interrupt the functioning of other machines in the next level of treatment. Mud trap and equalization tank falls under this stage. Next, primary treatment. Primary treatment is responsible in removing material that floats or readily settle out by gravity. Dissolved air flotation is used in this level. Next, secondary. Secondary treatment is essentially for biological treatment and widely used in wastewater treatment technology for the removal of dissolved and suspended organic compounds in industry. Aeration tank and clarifier tank is used in this level. Next up, solid handling. Solid handling is done before sending the solids to the quality alarm. Now let's see the functions of each unit operations. Mud trap. It removes heavier small particles such as sand and gravel. Equalization basically maintains and equalizes the flow of the influence. Next, the dissolved air flotation, where it acts in the combination of both physical and chemical treatment for the removal of solids and emulsion. In the secondary treatment, there is two unit operation, which is aeration tank. So aeration tank basically allows the bacteria to decompose the organic particles, which then clump to the sludge to settle. The clarifier then separates the treated effluents and settled sludge. Next, filter press. The filter press works in the solid handling category, where it separates the liquids and solids using pressure filtration, which then will be used to send it to the quality alarm. And also, one of the outlet for the clarifier will go to the next level, which is the tertiary treatment, to further removal of suspended and dissolved solids.
In the tertiary stage, the feed tank equalizes the water flow. Microfiltration modules removes tiny iron and fouling materials, organic or inorganic, that is originating from the pipeline. The water is then stored in a filtrate tank. It is later pushed into a two-stage reverse osmosis system. In the two-stage RO system, the concentrate from the first stage becomes the feed water for the second stage, and then the combining water from these two stages is the final product. It results in a clean and purified water that could be used to cool down heat exchangers and reactors inside the plant.
Thank you, Ara and Salman. So without further ado, let me proceed with the process economics and cost estimation for which the cost of the plant will be calculated. Moving on next, here I present you the capital expenditure for our plant. Here are the equipment that are used in our plant, and it's determined that the total purchase equipment cost in RM it's around 496 million. Next, we have the operating expenditure, the OPEX, and here we have the fixed and also the variable operating cost. And eventually, it is determined that by summation of the total direct and indirect cost, the total OPEX will be around 1.6 billion RM per year. Next, we have the economic analysis. So firstly, by selling our products, we are earning the total annual cost of 2.5 billion RM per year. In terms of the gross income, it will be around 937 million RM per year. And in terms of the economy, it's EP1 2.3 billion, EP2 2.1 billion, and eventually EP3 around 2.1 billion RM per year as well. Next, I present you the cumulative cash flow, and it is determined that the cumulative net cash flow is around 6.9 billion. And in terms of the rate of the return, ROR is calculated by using this formula, and it is calculated at 16%, which is more than the assumed MARR, which means that this project is profitable. Here I have the net present worth. So basically, net present worth, it means that it's the difference between the present cash flow inflow and also the cash outflow. And it is determined that the cumulative net present worth will be around 2.9 billion at a rate of 15%. Moving on next, let us look into the discounted cash flow rate or return, DCFRR. So basically, this is a measure of the maximum rate that a project could pay and still break even by the end of the project life. As indicated by the year 15, this cumulative net present worth is 0. And by doing so, it's determined that the maximum rate will be around 77.65. And it is determined by using trial and error method, or even better by using Excel GoSeek function. Lastly, let me show you the summary of this project economy evaluations. So before that, let us know about some assumptions. The life period is around 15 years, and the operating hours 800 years, annual revenue 50, 75, and 100% for the first, second, and subsequent years, and then the MARR is set to be around 15%. So let us see the summary of it. So by selling our ammonium sulfate and also the methanol, these are the cost distribution. We have the total expenses, income tax, investment cost, depreciation cost, and also the cost income, which is the total revenue and the salvage value. So let us see. In terms of the net present worth at 15%, we have 2.9 billion. So in terms of the rate of return, it is 16%, which is more than the MARR for 15%. So in terms of the cash flow, it determined that the payback period will be around 5.8 years, and the DCFRR, which is 77.65%, which means that it is more than MARR. So what can we conclude here is that this project, in terms of DCFRR, the payback period, which is short, and also the ROR, it means that this project is very profitable.
Hi, this is Salman, and I'm here to provide our final outcome and an overview of the things that we have presented. We have first provided 3 design alternatives in which alternative number 1 became unfeasible due to its high cost of hydrogen production, and alternative 3 is impractical due to its high utility cost. That is why we have gone with design alternative number 2, which is within the limits of CAR 2014. The plant produces over 32,000 tons of ammonium sulfate per year and 2 million tons of methanol annually. We have discussed about how heat integration and reactor optimization has led to further cost reduction. About 28 million ringgit per year is saved from these heat integration. Next, we have shown the PFD and the PNID of the plant which was designed, and we have added in the recommendations given to us last semester. A HAZOP study was performed on 3 specific nodes, while we have talked about the wastewater treatment for the plant and the commitment to follow regulations when it comes to wastewater treatment. And finally, we have performed economic analysis where we have found out that our plant has an income of 812 million ringgit per year with a rate of return of 6% and a payback period of less than 6 years. We believe that our plant is an attractive investment. In short, this project is attractive and it is feasible in terms of technical, economical, and environmental aspects. Thank you.